Um, I know that this is, I mean, I know I make it possible for people to attend, either in person or online, just for community sake. And also this, there's at least one student in the class who's doing an online degree program, so I actually have to offer it that way. But it's just my personal feeling that I hope that this is not like a trend where we have fewer and fewer people here. And this, aside from students who are in online degree programs, this is meant to be an in-person class. And it's there's something that's lost when that's very common teaching on. When I had to teach online during a pandemic, something that's lost when I'm just basically talking to a sea of black faces. So, I mean, again, I know I give the option, and don't officially imposing restrictions on it. I'm just saying, I think we all tend to gain more from it when there are more people. I'm just saying this out. Just say it. Okay. Now, this is the last section of this chapter on polynomial interpolation that I feel like covering. There are other sections in this chapter I just don't feel like covering. Osculatory interpolation. So, all chapter long, we've assumed that the x values for our interpolating polynomial are distinct. And now we're going to drop that assumption, where it would be possible to list an x value more than once among the interpolation points, which seems kind of strange, but there's actually a compelling reason to allow that. So let's suppose we have two x values that are distinct, the xi and xi plus 1, and here are the y values that go with them. And you let xi plus 1 approach xi. So we're taking this limit, in other words. So xi plus 1 approaches xi, and we examine this difference quotient, difference in y values over difference in x values. Well, each y value, if we think of that as the value of some function f as the corresponding x value, then our difference quotient becomes this. It's a difference quotient that, as you know from calculus 1, converges to a value of a derivative value. So this expression converges to yi prime, which is also f prime at xi. But because the interpolating polynomial also associates these y values and these x values, this difference quotient is also converging to the derivative of the interpolating polynomial at xi. So now, so the main thing to take away from this is this equality here, that when you have two distinct interpolation points approach each other, in the limit, what happens is not only does your interpolating polynomial agree with f at the x values, its derivative agrees also. So that's why we're dropping our assumption of all the x values having to be distinct, because it allows us to fit f of x in other ways. So we're not just matching y values, we can match derivative values. So we can capture more of the behavior of f of x. So this leads to what's called osculatory interpolation. So osculatory interpolation is when you have an interpolating polynomial that matches f of x at select x values and agrees with certain derivatives of f of x. Not just first derivatives like in this example here, but possibly higher order derivatives too. The term osculatory interpolation comes from the Latin word osculare, which means to kiss. So the x values approaching each other so they meet. And I have to mention that when I first learned about this topic, way back in 1988, when I took my first numerical analysis class at Purdue, taught by Sam Conti, who was the founder of the computer science department at Purdue, Department of Computer Sciences, and also the author of the textbook. And at the time, he was pretty old, he was nearing retirement. And hearing about this, talk about introducing his form of time interpolation based on the Latin word to kiss from a 70-year-old professor. I was like, not pretty at all. Yes. What?
We're learning about kissing that now, and then in history and mathematics, we learned about a cute number. Like,
yeah, cute
number, not acute, but cute.
Really, that's the thing.
Yeah.
Wow. I'm missing out. Okay. So here's an example of oscillatory interpolation. So here we have only two distinct interpolation points, x0 and x1. So we want our polynomial to equal the given y values at x0 and x1, just like the ordinary interpolation that we've seen. And then at x0, we want the first derivative to agree with some specified value, which I'll call z0. So that'd be like f prime of x0. And then we also want the second derivative of our interpolated polynomial to at x0 to equal some specified value. That's f double prime of x0. So at x0, we have three conditions. It has to match f prime, and f double prime. At x1, we only have one condition, the usual condition of y value. So normally, if I only had two interpolation points, and I only cared about matching y values, well, that would be a line defined by 2 points. But now I have two additional conditions for matching f and f prime and f double prime of a point. So now this polynomial has to be of degree at least 3, cubic. So it doesn't matter whether the x values are distinct or not. The bottom line is the degree of your interpolated polynomial is always one less than however many conditions you impose. We're just imposing different conditions in form. So how can we obtain this polynomial? So the simplest way, corresponding to the van der Waals matrix approach from the beginning of the chapter, we assume that our interpolated polynomial has this form, power form for a cubic. So now I set up a system of 4 equations for my 4 conditions, where I solve for my 4 unknowns, the 4 coefficients of my polynomial, a0, a1, a2, a3. So the first couple of conditions are what we've seen before from the van der Waals approach, where we plug in our x values into our polynomial and require that they equal the corresponding y values. So that's what we get for these first 2 equations. Third equation, we take the derivative of our interpolated polynomial. We evaluate that at x0 and require that it equals z0. And then we take the derivative again. Fourth equation, plug in x0, require that equal our f double prime value, which I'm calling w0. So once again, we have a system of 4 equations and 4 unknowns, is that we have different equations in case of matching derivatives. So then we go ahead and solve the system of equations. It's a little easier to solve because we now have some 0 entries in our matrix. So we can, so that's one way to proceed. But this still has the same kind of drawbacks as van der Waals in the case of distinct x values. It's still an expensive approach, on the order of n cubed operations for a polynomial degree n. We still have the issue of ill conditioning if the x values are clustered together. So we'd still rather not pursue that. Now, if we think about the other approaches we've seen for computing an interpolating polynomial, there's Lagrange and Newton. I'll talk about a Lagrange-like approach at the end, but really the easiest way to handle oscillatory interpolation is by adapting the Newton approach, divided differences. Okay. So how do we handle divided differences if some of the x values repeat? So what you do is, if at one of your x values you impose k conditions in total, like for example, in the example we had here, we had k equal 3 at x naught. We mapped a y value, y prime value, y double prime value. However many conditions you impose on a particular interpolation point, you have to list the point that many times in a divided difference table. Then, when you go to actually compute the divided differences, what's going to happen if you're doing oscillatory interpolation, you're bound to have a situation like this, where you want to compute this kind of divided difference, but xi is equal to xj, so then you have a 0 over 0 situation. So what you do when it happens is, you fill in the derivative value. So aside from that, it pretty much proceeds like it normally does for working with the Newton form. Now that's for a first derivative. If you have a higher order divided difference, just something like this, where again xi equals xj, what you have to do is, if your divided difference is of order k that you're computing, and these x values are equal, then what you'll fill in again is a derivative, kth derivative at that point xj, but don't forget to divide by k factorial. We're going to see examples of this, but I'm just giving you the basics of how you complete the divided. So I'll show you how it's done for this example right here that I was giving earlier. So this is the divided difference table for that example. So we have 3 conditions imposed at x naught and only 1 condition imposed at x1. So you list x naught 3 times, and then x naught just once. Then you list the corresponding y values in the second column, just like before. So in this column, we go to compute our first order divided differences. So this divided difference would come from these values, this minus this divided by this minus this, but everything's the same. So you fill in the first derivative value right here. And then the same situation happens with these points. Because normally you could take this minus this divided by this minus this, and that's 0 over 0 again, so you fill in the derivative in this spot also. Then, down here, the x values are distinct, so that's an ordinary first order divided difference, y1 minus y naught over x1 minus x naught. We have that. So now this second column is complete. We go to the next column. These are second order divided differences here and here. So normally this divided difference would be computed from these two. So you take this minus this divided by this minus this, but these are equal again. So you fill in 1/2 times the second derivative value. So don't forget to divide by whatever order derivative it is, you have to divide by the factorial of that order. So 1/2 f double prime at this point. And then you have, here we have an ordinary divided difference with distinct x values. So you take this first order divided difference minus this one, divided by x1 minus x0, and that gives us this expression here. That's beginning to get ugly. And then for a final divided difference, you're dealing with distinct x values, x1 and x0, so you just repeat this divided difference in a regular way. Expect a problem like this on the final. So are there any questions about how you handle a divided difference table for a case of non-distinct x values? Including any questions from the online ping gallery.
So this is the case, like this example that we're doing would be for what are the like 2 points that are, what are our points?
Okay, so your distinct x values are x0 and x1, but you have 3 conditions at x0 and only 1 condition at x1.
So it would be, we have the x and y values are both the same.
Yes. Yeah, so because we have this x value listed 3 times, you have a y value, that same, the corresponding y value also listed 3 times. The only time you would have that is if the conditions for your interpolant involve matching a y value, a y prime value, and a y double prime value at that point. So there are many different oscillatory interpolation situations. Like, let's suppose we have, okay, let's suppose we're talking about a cubic polynomial, so always 4 conditions. You could have, like we were doing before, 4 distinct x values only matching y's. You could have 1 distinct x value and matching y, y prime, y double prime, y triple prime at that point. Actually, one of the explorations in this section is about that kind of situation. You could have 2 and 2, x0 and x1, and you match y and y prime at each, which is called a interpolation that I'm about to talk about. So even if you consider it restricted up to a certain degree, there's many different scenarios. I don't know if that is a question at all, but
so could it be where we have so when it says, for example, and it says p of x naught equals y naught, and then p of x1 equals y1.
Yeah.
Could we have a case where we have more than just those 2 points, or is it always the case where we have 2 points there?
Oh, I mean, you can have as many distinct x values as you want. Is that what? So you just have to tally up, like, okay, here are all the conditions you're going to impose from your distinct x values matching at least a y value, and then any derivatives you want to match at any of these points, and you have full flexibility there. Like, that's why I gave this example where we have more conditions at one point than another. It doesn't have to be balanced. And then
but
once
it doesn't have to be inbounds.
What?
But it doesn't have to be inbounds.
No. In fact, I'm going to talk about a balanced case shortly. And once you figure out, okay, here's how many conditions you want, then the degree of your polynomial will be 1 less than the number of conditions.
And then the conditions would also include your just your f of your x value equaling your y value,
And your derivatives.
And then okay,
Yeah.
But it would be in how many derivatives you want. Like if you we can go to like third derivative as well.
Yes.
And then so if we wanted to have, is it always that like here it's an imbalance where we have all the with our conditions we have all the derivatives of for P of X naught, but if we have P of X1 and its derivatives, does it always have to be matching to, like, on here we had the second derivative, we went up to the second derivative, and then if we do P of X1, we go to the second derivative of that one?
Oh, we don't have to. Yeah.
But it can be, right?
Yes.
Okay.
Yeah. Yeah. So at each distinct x value, you can impose as many conditions as you want independently of the other points. Although one thing I want to make sure it's clear it's not allowed. Okay. At a certain point, I'll just call it x2. You cannot impose that, oh, I'm going to require that the derivative equals something, but I don't care about the y value.
Mm-hmm.
You have to start with the y value and then go down as many derivatives as you want to. You can't skip, because then we wouldn't know what to do in a divided difference table.
Derivatives build on each other.
Alika? Okay.
I have a side question, but might not be very important. But so if you scroll up, so if xi equals xj for a case order divided difference, fill in the case derivative at xj over k factorial.
Yeah.
So what is the reason behind the k factorial?
Okay, this actually relates to a theorem I mentioned last time, where a kth order divided difference, and we're talking even in case of distinct x values, is equal to the kth derivative at an unknown point over k factorial. So it's consistent with that result.
And then that was similar to the Taylor remainder?
Yes. Yeah, so basically it's a factorial coming from taking nth derivative of an nth degree polynomial and getting a factorial. And there were questions about how we do a divided difference in this case. Once you have the divided differences, the way you build a polynomial is the same as we've seen in the Newton case for distinct x values. So here what you can do is you can go through the top row of your divided difference table, those are your coefficients, and then so y naught is a constant term, and you multiply, add on z naught times x minus x naught, the first point, then you move to the next one, 1/2 w naught. And because x naught is listed twice, we're including the first two interpolation points in the list, you're going to get x minus x naught squared. And then when you get to a final divided difference, normally you would do x minus this times x minus this and times x minus this. And you still do that. It's just that all because your factors are the same, so we see in this case we have x minus x naught cubed. So what happens when you do oscillatory interpolation and you use a divided difference table to get it, you end up with certain linear factors raised to higher powers if you have multiple conditions imposed on them. Actually, the highest power you can have equals how many conditions you impose at that one point. For the remainder of the time, I'm going to focus on a special case of oscillatory interpolation that's particularly well known, and that is called Hermite interpolation. I think I'm pronouncing it correctly. To be sure. So the idea behind Hermite interpolation is that at each one of your distinct x values, you impose that the interpolating polynomial must match a prescribed y value and a y prime value. So here it's balanced. And you only match to the first derivative, but you do it at every distinct point that you have. So if your distinct x values are x naught, x1 up to xn, so you have n plus 1 distinct x values for your interpolation points. And at each one of these points, you impose two conditions, matching y and y prime. So you end up with a total of 2n plus 2 conditions that the interpolating polynomial must satisfy. So the Hermite interpolating polynomial will have, if you have these n plus 1 points, will have a degree of 2n plus 1.
Why is it considered an osculatory interpolation?
Because you're matching derivatives.
Oh, so it isn't like they're distinct and non-distinct.
Well, so you can think of it this way, and this is what you will see when we actually compute these things. Think in terms of like in your derived difference table, you take each of these distinct x values and you list it twice. So you can think of it as, okay, we're constructing a 2n plus 1 degree polynomial, and you can think of it as n plus 1 distinct x values, or you can think of it as, since it's degree 2n plus 1, you have 2n plus 2 interpolation points, but they come in pairs.
So the non-distinction would be in the table.
Yeah, yes. And then, in fact, that's what you'll see. Yeah. In a little bit. So here this is the error formula for the Hermite interpolating polynomial. And this is what we saw last time, just for ordinary Lagrange interpolation. And quite similar. But they're totally consistent with one another, because whatever the degree of your interpolating polynomial is, you add 1, and that's the order of derivative that you have in your error formula on one point. And then that degree plus 1, you're dividing by that factorial. And whereas in Lagrange interpolation, you have x minus each interpolation point, well, these linear factors multiplying together. Here you have those same factors, but they're squared, which makes perfect sense because you're listing each point twice. So in fact, if you were performing Lagrange interpolation and you had 2n plus 2 distinct x values, but then you let half of them approach the other half, like you took the limit, then what you see from this error formula would literally converge to this. So even though I've already shown you how you can handle the oscillatory interpolation using a divide difference table, I'm going to show you how you compute handle Hermite interpolation, how you compute the Hermite interpolating polynomial using first divide difference table, and then a different approach that is for life Lagrange. So for divide difference, I'll just step through an example. Once again, we have two distinct x values, so x0 is 0, x1 is 1. At x0, we have to match function f value and f prime value. And then at x1, we also match an f value and an f prime value. And given the f and f prime values I've chosen, so f is actually equal to 0 at both x values, and the derivative is equal to 1 at both x values. So this would be a function that actually satisfies all those conditions. Sine 2 pi x all over 2 pi. Okay. So we have 4 conditions imposed, 2 at x0, 2 at x1. So we're going to have a cubic polynomial. We're going to have 4 x values listed in the table. Now, I've identified the interpolation points as x0 and x1, but for a table, I'm going to define 4 z values that are not distinct. So these are 4 interpolation points that I'll use. for a divided difference table. So here we have our first distinct x value that's labeled as z0 and z1. And then my other distinct x value, which was previously labeled as x1, but that's also z2 and z3. Oh, something is wrong here. These should be equal. Oh wait, no, never mind. It's not wrong. Walk up to the TV. Been a long day. I've been here since 8 a.m. Okay. Notice f of x naught is 0. F of x1 also 0. In other words, all the y values are 0. So that's why this column is all 0. Then we go to the first order divided differences. So for this one, we work with these y values and these z values, but they match. So you fill in derivative value, f prime at x naught, which is 1. And you do the same thing down here. We have this does the divided difference, this minus this over this minus this. But again, those points are the same. So we list the derivative value at x1, which is also 1. And then for this divided difference, we have 0 and 0 for y values, this minus this, but divided by distinct z values, 1 minus 0. So that divided difference is 0. Once you get past this column that has the first order divided differences, at that point it's like an ordinary divided difference table where you have all distinct points, because for the higher order divided differences, you will have distinct z values in your denominator. So then just complete the divided difference table there, like done before. Are there questions about how this divided difference table is filled in? Now we look at the top row of coefficients. By difference 0, 1, minus 1, and 2. Our constant term is 0. And then we have our next coefficient 1 times x minus z naught. Then plus minus 1 times x minus z naught times x minus z1. And then our last divided difference 2 times x minus z naught, x minus z1 times x minus z2. And then we fill in that z naught and z1 are both equal to 0. And z2 is equal to 1. So just filling in the particulars, this is what we wind up with. And then after multiplying everything out and getting everything, well, it's not quite all the way to power form, but just getting rid of all the zeros, then this is what we get. Okay. I told myself that I wasn't going to do a MATLAB demonstration today. But now I feel I need to.
Now tell us, you're gonna set up another diary?
Yes. But hopefully this will be a quick one. Because I want to show you the graph of the underlying function here, sine 2 pi x over 2 pi, and the interpolating polynomial. Okay. Okay. So, and you don't have to follow along now, I'll post a diary later, and the graph that I'm going to produce.
Rebecca has the urge. No?
It's a massacre. This is a massacre.
I hope not. Okay, so, so I'm gonna plot the original underlying function and the Irving polynomial on the interval 0 to 1. So I'm gonna define a vector of x values using Lin space. And in this case, I'm just plotting on 0 to 1, so I think 100 points should be enough. Okay. And at least I already have the interpolating polynomial defined, so I can just go ahead and plot it. First, I'll plot the function that I'm trying to match. Okay. Make sure I don't have any figure windows open, so do close all.
Close all.
And then I'm going to plot. So my function that I want to plot is, my f of x is this, sine of 2 pi x divided by 2 pi. Okay, so sine 2 x over 2 pi. I'll plot that in blue. And that's the default color, but anyway. Okay, let's see what that looks like.
2 times pi.
Okay, so that's a function that I want my interpolating polynomial to match, and it needs to, agree with the function value and the derivative at x equals 0, and over here too at x equals 1. What happens in between? Who knows? We'll find out. Okay. Now, I need to do a hold on. I want to see both plots in the same graph. And then I need to look up my polynomial that I'm going to plot. And okay, here it is. X minus x squared plus 2x squared times x minus 1. Okay, so I can include that in my plot statement. So x, and then I'm going to have x minus x dot squared. X is a vector. If I do x up arrow 2, that's going to be an error, but dot squared for component-wise squaring. And then plus 2 times x squared, and then I have to multiply by x minus 1, so that will call for a dot star x minus 1. And I'm going to plot that using a red dashed curve.
X, comma x minus x.
And assuming the Irving interpolating polynomial is computed correctly, I've never done this before, so
Wait. Still trying.
They told you to think something.
it's all self-interested. You have it?
How does it look? X,
Okay, now, so now we can see the graph here. And so on one hand, this interpolating polynomial is not a great approximation of sine 2 pi x over 2 pi. But what it does get right what it absolutely needs to. So certainly the values at x equals 0 and x equals 1 agree with each other. But we also have that notice the slope of a curve. matches and x equals 0 and x equals 1. I'm not going to do this here, but I'll bet if I was to take the derivative of both of these functions and plot them, then I actually would see the y values at those two points match for a derivative.
So the more oh no, wait. I want to think that the more conditions you have, the more accurate your graph will be, but what do you call that phenomenon?
Obvious.
Yes.
Okay. It will match the function better near the point at which you impose the conditions.
Yes.
But away from that point, yeah, it's going to be a problem.
It does play a role here.
Yeah. One thing that I found very aggravating, I need to check on this. As far as I know, polyfit that computes the interpolated polynomial for you requires it takes values into state or state. I can't talk anymore. It will not do osculatory for you. Now there's a pretty impressive code repository called MATLAB Central, where anyone can contribute to it, like they implement certain algorithms that are not already available in MATLAB. It's possible someone might have written a meter osculatory interpolation function for bats. There's enough information I've given here in class to be able to make that happen. I still don't know if anybody has, because
Extra credit.
You'd be called the whole world. I actually have found osculatory interpolation, and not just for me, helpful in my own research. Yeah, I'm surprised that MathWorks themselves have not implemented that. Oh, well, they also use Vandermonde and Polyfit, so. Yeah, because if you're using a divided difference, then it'd be pretty easy for them to make that leap. But, oh well. Okay. Yes, a lot of times if I just Google like whatever algorithm I'm looking for and then MATLAB, then often something from MATLAB Central pops up. So if MATLAB itself doesn't have what you need, maybe someone else has done it for you. And in some cases, that's really been very helpful. It's like if I'm running a research article about like some algorithm of mine, and I want to compare to someone else's algorithm, it's not always easy to just implement that myself. And sometimes I have, but other times I've been able to find someone else's implementation that's readily available, and I just cite them, of course, and I get what I need. No fuss, no muss. Okay, and okay, so end this MATLAB demonstration here. But I'll post this very short diary and this plot in Canvas afterwards.
It wasn't as
Undeniably short. Carry on.
It wasn't as pretty like the visual, but the coolness of like the math matching the visual.
Yes.
You have to look close, like I like the appreciation of like the math matching the visual, but
Yeah.
the images last time were just
Yeah. Okay. Okay. Now, the last part. I know that at least one of you has already seen this. Sorry. Is so what is a way to generate an interpolating polynomial that's more like a Lagrange form? So here's the Lagrange form that we've seen before. So Pn of x is equal to a summation of the y values, or your f of x values, times the corresponding Lagrange polynomials that are equal to 1. This Lagrange polynomial will be equal to 1 at xj equal to 0 at the other xi. So we're going to have a form like this for the Hermite case, but it has to take into account the derivative values. Okay, so here's the Lagrange polynomial property that is mentioned. So here's what we have for a Reed case. So your Reed interpolating polynomial is equal to a summation of f values times these polynomials, which are called a fancy h, that are degree 2n plus 1, plus the f prime values times these polynomials that are also degree 2n plus 1, the fancy k. So I need to show you how we get these. And that comes from the conditions they have to satisfy. So let's suppose I substitute x equal to xi in here. So we're going to evaluate all of this at xi. Well, the result of this summation, when x equals xi, has to be f of xi. That means that if I plug x equals xi in here, into these fancy k's, all of these have to be 0. So there'll be no derivative values creeping in there. So the fancy k's, right here, must be equal to 0 at all interpolation points. Meanwhile, the fancy h polynomials, these act like Lagrange polynomials. If I plug in x equals xi, when j is equal to I want it to equal 1. So I would get f of xi. At any other x value, these should need to be 0. So these fancy h polynomials at the interpolation points act just like Lagrange polynomials do. So far I've covered these conditions and these conditions. But then we have to think about the derivative. If I take the derivative of this whole equation, so now I have h2n plus 1 prime at x of x, and then I substitute x equals xi, I want that to equal f prime at xi. Now the only things that get differentiated here are the fancy h's and the fancy k's. So I need the fancy h polynomials, I need their derivatives to be equal to 0 at all the interpolation points. So that's why I can't just use Lagrange for the fancy h ones, because I need them to satisfy these conditions too. And as for a fancy case, when I take a derivative of them, I need the derivatives to be Lagrange-like. So each one of these fancy k polynomials, polynomial j at xj is equal to 1. Derivative of polynomial number j at xi must be 0 when I is not equal to j. So here we have these Lagrange-like conditions, but basically we need to make sure that these polynomials don't step on each other's toes by prescribing where either they or their derivatives must be equal to 0. Any questions about these conditions that these polynomials have to satisfy? I know it's a lot. Yeah, that's symmetry to it. So now we have prime polynomials that will satisfy all of these conditions. And fortunately, Lagrange polynomials will be very helpful in figuring that out. Now, so we're going to use the fact of Lagrange polynomials. Like Lagrange polynomial j is equal xi is equal to 0 whenever I is not equal to j. And if we look at both of these sets of polynomials, if I have polynomial number j and I plug in xi when I is not equal to j, then the polynomial itself and its derivative both equal to 0. That's true of the fancy h's and the fancy k's. So right now I'm not focusing on xj for polynomial j. That we'll handle that later. But the bottom line is, just as Lagrange polynomials are equal to 0 for I not equal to j, and because these polynomials, fancy h's and fancy k's, have to satisfy the same conditions, but for themselves and their derivatives, what that means is the factorization of both the fancy h's and the fancy k's must include the Lagrange polynomial squared. So the thing I'm using here is if I have a polynomial and I need to be equal to 0 at some point a, then its factorization would include x minus a. If I want the derivative to also be equal to 0 at a, then the factorization would include x minus a quantity squared. So in general, when a polynomial's factorization includes x minus a, the whole thing raised to some power, that power is the multiplicity of the root. That indicates how many derivatives also have that point as a root. So because I want the polynomial and the derivative to be equal to 0 at the same place where the Lagrange polynomials are known to be 0, by including the Lagrange polynomial squared as a factor in both sets of polynomials, I end up ensuring that most of these conditions are satisfied. Now, how many conditions have I satisfied? Lagrange polynomial squared is of degree 2n. These polynomials, the fancy h and fancy k's, those are of degree 2n plus 1. So what remains in the factorization are polynomials of degree 1. And those have to satisfy the remaining two conditions, because these polynomials that are indexed j, I've ensured that when I plug in xi for I not equal to j, I'll get 0. What I need to make sure of, like for these, if I plug in x equal xj, I need to get 1. And if I take a derivative and plug in xj, I'll get 0 for these guys. For these, it has to be the opposite. If I plug in x equal xj, I need to get 0. And if I take the derivative and plug in xj, I need to get 1. So, in fact, so here are the conditions that I just mentioned right here, at least for the fancy h's have to satisfy these conditions, and the fancy k's have to satisfy these conditions. Now I need to step you through these. So, all right. So if I have polynomial for fancy h's, if I have polynomial number j, I plug in xj. What's that going to be? Lagrange squared at xj, but that's equal to 1. Because it's xj plugged into polynomial j. And then I have this left over, so at xj, it must be equal to 1. Now, if I take the derivative, then by product rule and general power rule, I get this monstrosity. Now, Lagrange polynomials are equal to, Lagrange polynomial j is equal to 1 at xj, so that does simplify things a little bit. I end up with this, and that has to be 0. So now Pj has the polynomial of degree 1 that has satisfied this condition and this condition. And so what I could do is, I could, for instance, say Pj of x is equal to like AJX plus BJ, sort of two unspecified coefficients. I have a system of two linear equations in two unknowns to solve, and this is the solution. If you really want to, you can work out the algebra on that. Meanwhile, for fancy k's, so if I plug in x equals xj, I get this. Lagrange polynomial is equal to 1, so really it reduces to this. And at xj, it must be equal to 0. If I take the derivative, I get this whole expression. But qj of xj is 0, so I'm taking that into account down here, which causes this whole term to go away. And this Lagrange polynomial is equal to 1 at xj. So I'm left with this, that's equal to 1. So again, I have two equations to solve for two coefficients of QJ, because it's a degree 1 polynomial, and it just turns out to be x minus xj, satisfies both of these. So now I have my formulas for my fancy h's and my fancy k's that they both involve Lagrange polynomial squared. So I do have a Lagrange-like form for the Irving polynomial, but these are pretty cumbersome. I mean, I 10 out of 10 would not recommend using this approach to compute the Irving polynomial, rather do a divided difference table. But this is out there, so figured I'd let you know about it. Plus, it's fun to just come up with these, or show where they come from. Okay. And I believe that's the end of the notes. That's it. We have time for any homework questions. I know there's some assignments trying to pile up again. There was a reprieve around the time of the midterm, so I make sure to stay caught or if they go down behind again. So hopefully the next few days I'll catch up. Once y'all talk along me.
We were behind and now we're trying to catch up.
Yeah. Anything either from here or online? Oh, really? How do I pause until it gets super awkward?
I heard somebody yesterday explaining something in physics, like to someone else, it's like a non-math person.
Yeah.
It's in marketing. And he was saying something, there's something about like, in this case it's like this, but in this one it's like in 3 dimensions, and
Yeah.
you pause. Are you pausing for effect?
Yeah.
Like, are you pausing because
Yeah.
I'm pausing for effect?
Oh. Yeah, it's not much of an effect. But I guess I should thank y'all for not being like my trig class where I'd be at the board writing and I could hear behind me. Multiple people. Yes, I know, the suffering is just as great for me, I assure you.
Improve things in there a lot too.
I've started to just because I'm bored. So, I mean, yes, I'm busy solving problems and so forth,
Yeah.
but not roughly in time, but I want to make it more mathematically interesting for me and they can just go.
Yeah, someone, maybe one person out there enjoys that.
Yes.
He said out there, like it wasn't in a classroom, it was out in the world.
Well,
Well, it's a pretty large classroom.
so, yeah.
Still.
Yeah, but instead I hear things like, oh, my brain hurts. Okay, then I guess we're done for today. Then numerical differentiation coming up next time.
There will be no super Fs. There will be